The morning of August 9, 1945, a Type 97 Chi-Ha medium tank sat motionless in a testing yard outside Tokyo, its 25mm frontal armor plates already scarred from previous trials. Japanese Imperial Army engineers had gathered to witness something that would fundamentally challenge their understanding of anti-tank warfare. In their hands, they held a captured American M9A1 rocket launcher, a weapon their intelligence officers had dismissed as propaganda just months earlier. The test would take less than 3 minutes. The conclusions would shake Japanese armor doctrine to its foundation. For 3 years, Japanese tank designers had operated under a comfortable assumption. Their armor was sufficient because Allied infantry possessed no portable weapons capable of defeating it. The Type 97, Japan's most common medium tank, featured frontal protection that Japanese metallurgists considered adequate against anything short of direct artillery hits. American infantry carried rifles, machine guns, and grenades. None of these threatened a properly deployed tank. The captured bazooka represented something entirely different, a shoulder-fired tube that could punch through more steel than the tank's entire frontal plate thickness. If the weapon performed as American technical documents claimed, every assumption underlying Japanese armor design would prove catastrophically wrong. The test began at 0900 hours. A Japanese Army lieutenant, trained hastily on the weapon's operation from translated American manuals, knelt 40 meters from the stationary Chi-Ha. He loaded a single M6A3 rocket, shouldered the tube, and aligned the crude iron sights on the tank's glacis plate. The electrical trigger completed its circuit. The rocket motor ignited with a sharp crack, propelling the 3-pound warhead forward in a streak of white smoke. Impact occurred 1.2 seconds later. The shaped charge detonated on contact, transforming its copper cone liner into a hypervelocity jet, moving at approximately 25,000 feet per second. This jet, behaving more like pressurized liquid than solid metal, carved through the Chi-Ha's 25mm frontal armor as if the steel were wet cardboard. The penetration hole measured 4 inches in diameter, with glowing edges where the copper jet's extreme temperature had melted the surrounding metal. Japanese observers approached cautiously, peering through the opening into the tank's crew compartment. The jet had continued through the interior, puncturing the rear armor from inside before dissipating. Total penetration depth, 5 inches of homogeneous steel, plus whatever internal components stood in the weapon's path. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Colonel Takeo Nakamura, chief of the Imperial Army's Armor Technical Bureau, examined the penetration hole with growing unease. He had personally approved the Chi-Ha's armor specifications in 1937, confident that 25mm of face-hardened steel provided adequate protection against any infantry portable weapon. The bazooka had just invalidated 8 years of Japanese tank design philosophy. Nakamura ordered immediate additional tests. Over the next 6 days, Japanese engineers fired 17 more captured American rockets at various Japanese armored vehicles, documenting penetration performance that consistently exceeded their worst projections. The crisis facing Japanese armor development in August 1945 was years in the making, rooted in decisions made when Japan's war against China seemed the only military challenge that mattered. Japanese tank design had prioritized different characteristics than European armor: lightweight for maneuverability on poor roads, low profile for concealment in infantry support roles, and mechanical reliability in tropical climates. Armor protection ranked as a secondary consideration. Japanese tanks were built to support infantry against other infantry, not to engage enemy armor in decisive tank versus tank battles. This philosophy made strategic sense in the context of the China campaigns during the 1930s. Chinese nationalist forces possessed virtually no armor and limited anti-tank weapons. Japanese tanks faced rifle fire, machine guns, and occasional artillery. The Type 97's 25mm armor proved more than adequate for these threats. The tank's real vulnerabilities, mechanical breakdowns, and fuel supply mattered more than armor thickness. Japanese Army doctrine emphasized mechanical reliability and fuel efficiency over protection, assuming infantry would never possess weapons capable of threatening tanks beyond throwing distance. The Pacific War's outbreak in December 1941, initially, seemed to validate these priorities. Japanese armor overwhelmed British and American forces in Malaya, the Philippines, and Burma. Allied infantry, equipped primarily with rifles and machine guns, could do little against even lightly armored Japanese tanks. The few British anti-tank rifles encountered proved ineffective, their solid shot rounds bouncing harmlessly off the Chi-Ha's frontal plates. Japanese tank commanders developed confidence bordering on complacency. Their armor was sufficient because the enemy lacked weapons to challenge it. American bazooka development had proceeded along a completely different trajectory, driven by the desperate need to counter German armor that made Japanese tanks look like toys. When Colonel Leslie Skinner and Lieutenant Edward Ewell created their crude rocket launcher prototype in May 1942, they were solving a problem Japanese designers had never seriously considered. How could a single infantryman destroy a well-armored tank without committing suicide in the attempt? The shaped charge warhead technology, the electrical firing system, even the basic concept of a recoilless launch tube, all emerged from American efforts to defeat Panthers and Tigers, not Chi-Has. The weapon's first combat deployment came during Operation Torch in November 1942, when American forces landed in North Africa. Initial results proved mixed. Untrained crews achieved poor hit rates, and many weapons were captured intact by German forces, who would eventually reverse-engineer them into the superior Panzerschreck. But as American infantry gained experience and training improved, the bazooka's effectiveness increased dramatically. By 1944, properly trained bazooka teams achieved kill rates exceeding 60% against German medium tanks when firing at side or rear armor. Japanese intelligence monitored these developments with detached interest. Reports from German sources described the bazooka's capabilities, but Japanese analysts dismissed the weapon as irrelevant to Pacific operations. Their reasoning followed a simple logic. Japanese tanks would never face bazookas because Japanese strategy focused on defensive operations from fortified positions, not mobile, armored warfare. Infantry anti-tank weapons didn't matter if you weren't using tanks offensively. This analysis would prove catastrophically short-sighted. The first Japanese encounter with American bazookas occurred during the Saipan campaign in June 1944. Japanese armor, including Type 97 Chi-Ha and Type 95 Hago light tanks, counterattacked American positions in the largest Japanese tank operation of the Pacific War. Marine Corps bazooka teams, positioned in carefully prepared defensive positions, engaged the attacking armor at ranges between 50 and 100 yards. The results shocked Japanese survivors. Tanks that had seemed invulnerable against Chinese and early war Allied forces burned after single rocket hits. Crews who escaped reported penetrations that seemed impossible from man-portable weapons. Japanese after-action reports from Saipan described the bazooka encounters in terms suggesting disbelief. Tank commanders reported being engaged by what they initially thought was artillery, only to realize the projectiles came from individual infantrymen. The psychological impact exceeded the physical damage. Japanese tankers had operated under the assumption that infantry posed minimal threat beyond grenade-throwing range. Suddenly, every American position within 200 meters represented a potential tank killer. The captured bazookas, arriving in Japan for technical evaluation in late 1944, came from various Pacific battlefields. Some were recovered from destroyed American positions on Peleliu, others from crashed aircraft or sunken landing craft. Japanese intelligence officers treated these specimens with the careful attention usually reserved for enemy aircraft or naval technology. The weapons represented a fundamental shift in infantry capabilities that Japanese military planners had failed to anticipate. Initial examination revealed engineering philosophy completely foreign to Japanese weapons development. The bazooka was almost absurdly simple: a steel tube, crude sights, wooden shoulder stocks, and an electrical firing circuit using a flashlight battery. Total manufacturing cost was estimated at less than $5 American. Japanese engineers, accustomed to precision-machined weapons requiring skilled craftsmen, found the crude construction almost insulting. Yet the weapon's battlefield effectiveness was undeniable. American industry had created a weapon that any factory worker could assemble, any soldier could operate, and any tank commander had to fear. The shaped charge warhead technology particularly intrigued Japanese explosives experts. Japan had developed its own shaped charge weapons, including the Type 3, an anti-tank grenade and various magnetic mines, but these required soldiers to approach within arm's reach of enemy armor. The bazooka delivered a similar explosive effect from standoff range, transforming the tactical equation. A Japanese soldier with a Type 3 grenade faced near certain death, attempting to attach it to an American Sherman tank. An American soldier with a bazooka could engage from covered positions with reasonable survival probability. Japanese technical documentation from these evaluations survives in fragmentary form, much having been destroyed during the war's final months. However, post-war interrogations of Japanese ordnance officers revealed the conclusions reached during August 1945 testing. The bazooka represented a weapon system Japan could not effectively counter given its current industrial and tactical situation. Japanese armor was fundamentally inadequate against shaped charge weapons. Developing equivalent Japanese weapons would require Felice's trote, industrial resources, and time that no longer existed. The mathematics of penetration proved particularly damning. The M9A1 warhead, loaded with Composition B explosive, generated a copper jet capable of defeating up to 5 inches of homogeneous steel armor under optimal conditions. The Type 97 Chiha's frontal armor measured just 25 millimeters, approximately 1 inch. Even accounting for face hardening and sloped armor angles, the Chiha's protection was inadequate by a factor of 3 to 4. The Type 3 Chi-Nu, Japan's most heavily armored production tank, featured 50 millimeter frontal armor, still insufficient against direct hits. Japanese engineers recognized that simply thickening armor was not a viable solution. Increasing the Chiha's frontal protection to 6 inches would require adding approximately 5 tons of steel, making the tank immobile with its existing engine and suspension. Japan's industrial capacity in 1945 could not produce new heavy tank designs in meaningful numbers. The nation's steel production had collapsed to less than 30% of 1944 levels due to American bombing and naval blockade. Every ton of steel allocated to tank armor meant less steel for aircraft, ships, or fortifications. The captured bazooka also revealed the scale of American industrial advantage in ways that transcended simple production numbers. The weapon's electrical firing system used standardized batteries available in any American hardware store. The rocket motors used propellant compositions, requiring chemical plants that Japan no longer possessed. The shaped charge liners demanded copper of purity that Japanese refineries struggled to produce. Even if Japanese engineers designed an equivalent weapon, manufacturing it at scale would prove impossible given the collapsing industrial infrastructure. Colonel Nakamura's final report to Imperial Army headquarters, completed in late August 1945, recommended several desperate measures. Existing Japanese tanks should avoid direct engagement with American infantry whenever possible. Anti-tank tactics should emphasize dug-in positions where tanks operated as mobile pillboxes rather than maneuvering vehicles. Development of indigenous rocket launchers should proceed, but expectations must remain realistic given material shortages. Most significantly, Nakamura recommended that Japan acknowledge its armor development had failed to keep pace with Allied anti-tank weapon evolution. This admission carried implications far beyond tank design. Japanese military planning for homeland defense assumed that armored counterattacks would play crucial roles in defeating American invasion forces. If Japanese tanks could not survive against American infantry weapons, this entire defensive strategy required reconsideration. The captured bazooka represented a single weapon system, but its existence exposed systemic failures in Japanese military technology development that extended across multiple domains. The timing of these realizations added bitter irony. By August 1945, Japan's situation had deteriorated to the point where improved tank design or tactics made little practical difference. American strategic bombing had crippled Japanese industrial production. The naval blockade had severed access to raw materials. Even if Japanese engineers had devised perfect solutions to the bazooka threat, implementing them was beyond Japan's remaining capabilities. The captured weapon revealed how thoroughly Japan had lost the industrial and technological race that ultimately determined the war's outcome. Japanese tankers examining the bazooka understood they were seeing the future of armored warfare, a future where infantry portable weapons could defeat any armor thickness that practical engineering could mount on a mobile vehicle. This realization would influence post-war tank design globally, driving development of composite armor, reactive armor, and active protection systems. But in August 1945, Japanese officers examining penetration holes in their best tanks simply recognized that their armor had become obsolete before the war even ended. The psychological dimension of this discovery cannot be understated. Japanese military culture emphasized spiritual superiority over material advantage. Tanks were extensions of the warrior's will, protected more by courage and skill than by mere steel. The bazooka reduced this philosophy to bitter ashes. No amount of courage or skill could prevent a shaped charge jet from carving through inadequate armor. The weapon represented industrial warfare's brutal truth. Sufficient material advantage rendered traditional military virtues irrelevant. The technical specifications Japanese engineers documented during their August 1945 testing revealed uncomfortable truths about the gap separating Japanese armor development from Allied anti-tank weapon evolution. The Type 97 Chi-Ha featured maximum armor thickness of just 25 mm on most surfaces, with the improved Shinhoto variant reaching 33 mm. Against American bazookas penetrating 5 inches, roughly 127 mm, of homogeneous steel, Japanese armor protection proved inadequate by factors approaching 5 to 1. Japanese metallurgists examining the bazooka warheads discovered explosive chemistry that their own munitions programs had never attempted at scale. The composition B filling, a mixture of 60% RDX and 40% TNT, represented explosive technology that Japanese chemical plants lacked the capability to manufacture in quantity. Japan had developed its own shaped charge weapons, including the Type 3 anti-tank grenade, but these used conventional explosive fillings derived from picric acid compounds developed during the Russo-Japanese War 4 decades earlier. The copper cone liner inside the bazooka warhead particularly impressed Japanese weapons experts. American metallurgists had standardized on oxygen-free high-conductivity copper sheeting drawn to precisely 0.042 inches thickness. Japanese copper production, hampered by naval blockade and strategic bombing, struggled to maintain even basic electrical wire manufacturing. Allocating scarce high-purity copper to single-use munitions represented a level of material abundance that Japan's contracting war economy could not replicate. The shaped charge phenomenon itself was not unknown to Japanese engineers. German technical exchanges during 1940 and 41 had included documentation on hollow charge weapons, and Japanese ordnance experts had conducted their own penetration experiments. But the bazooka demonstrated how Americans had industrialized the technology, creating weapons simple enough for mass production, yet sophisticated enough to threaten any armor thickness that practical mobility considerations allowed. Japanese testing protocols during August 1945 followed methodical procedures that would have made peacetime researchers proud, despite the nation's desperate military situation. Engineers fired captured rockets at precisely measured angles, documenting penetration depth, hole diameter, and internal damage effects. They tested against various armor types, including face-hardened plates, rolled homogeneous steel, and cast armor sections salvaged from disabled Japanese tanks. Every test confirmed the same grim conclusion. Japanese armor could not withstand direct hits from weapons that American infantry carried as standard equipment. The standoff distance requirement, the gap between warhead nose and target surface that allowed the shaped charge jet to form properly, revealed sophisticated engineering hidden beneath the bazooka's crude appearance. The elongated nose cone extended approximately 6 inches ahead of the explosive charge, ensuring optimal jet formation regardless of impact angle variations. Japanese engineers noted this feature with particular interest, recognizing it as a solution to problems their own shaped charge weapons had encountered. Japanese magnetic mines often failed to penetrate effectively because they detonated too close to the target surface, preventing proper jet formation. Colonel Nakamura's technical staff calculated theoretical countermeasures during late August meetings at the Army Technical Bureau headquarters. Spacing armor, 2 plates separated by an air gap, could disrupt shaped charge jets by forcing them to penetrate twice while traveling through air that dispersed the jet's coherence. German tanks had begun incorporating this feature in 1944, but adding spaced armor to existing Japanese tanks would require extensive redesign and manufacturing capacity that no longer existed. New tank production in August 1945 had effectively ceased, with remaining factories producing spare parts for existing vehicles rather than complete tanks. Alternative defensive concepts proved equally impractical. Reactive armor, explosive plates that detonated outward when struck, could theoretically defeat shaped charges by disrupting jet formation. Soviet engineers would eventually develop this technology during the Cold War, but in 1945 Japan, developing entirely new armor technologies while the nation's industrial infrastructure collapsed, represented fantasy rather than feasible engineering. Japanese technical staff could document solutions on paper that national capabilities could not implement. The American industrial model, revealed by the bazooka's existence, carried implications extending beyond the weapon itself. United States forces equipped entire infantry divisions with thousands of rocket launchers manufactured at costs measured in single-digit dollars. Japanese intelligence estimated American bazooka production exceeded 50,000 units monthly by 1944. Japan's entire wartime tank production, all variants combined, totaled approximately 6,000 vehicles. A single month of American anti-tank weapon production outnumbered Japan's complete armored vehicle output for the entire war. This disparity reflected fundamental differences in industrial philosophy that Japanese planners had catastrophically underestimated when committing to war in 1941. American manufacturing emphasized standardization, interchangeable parts, and assembly line production that allowed semi-skilled workers to produce sophisticated weapons at remarkable rates. Japanese industry retained craft-based manufacturing approaches where skilled workers hand-fitted components to individual specifications. This produced weapons of excellent quality but terrible quantity. A Japanese tank required approximately 12,000 man-hours to manufacture. American Sherman tanks rolled off assembly lines every 45 minutes. The bazooka's electrical firing system demonstrated American technological pragmatism that contrasted sharply with Japanese design philosophy. The weapon used standard batteries, available commercially, required no special training to replace, and functioned reliably across wide temperature ranges. When batteries failed, operators simply installed fresh ones from standardized supplies. Japanese weapons designers favored mechanical systems requiring careful maintenance and skilled armorers. This approach worked well with professional soldiers but proved problematic, as experienced personnel became casualties and replacements lacked equivalent training. Japanese after-action reports from Saipan, Iwo Jima, and Okinawa documented the psychological impact bazookas inflicted on tank crews even beyond actual casualties. Tank commanders reported that crew effectiveness degraded severely in areas where bazooka teams operated. Drivers became hesitant, gunners fired prematurely at suspected positions, and commanders made tactical decisions prioritizing survival over mission objectives. The weapon transformed the relationship between infantry and armor from one-sided dominance to mutual threat, forcing Japanese tanks into defensive postures that negated their mobility advantages. The Saipan counterattack on June 15, 1944, provided particularly sobering lessons that Japanese armor officers studied intensively. Colonel Takashi Goto's 9th Tank Regiment and Colonel Yukimatsu Ogawa's 136th Infantry Regiment launched a combined offensive involving nearly 60 Chiha and Ha-Go tanks against U.S. 6th Marine Regiment. American defensive positions included carefully coordinated bazooka teams positioned in depth, ensuring attacking tanks faced multiple rocket launcher positions from varied angles. The offensive collapsed within hours, with Japanese tank losses exceeding 70%. Marine after-action reports credited bazookas with the majority of tank kills, noting that shaped charge warheads proved devastatingly effective against the thin side and rear armor Japanese tanks presented while maneuvering. Japanese tactical doctrine for armor employment had emphasized speed and surprise, using tanks as mobile infantry support rather than engaging in armor versus armor battles. This approach worked effectively in China and during early Pacific campaigns, where Allied forces lacked concentrated anti-tank defenses. Bazookas invalidated these tactics by providing every American infantry company with organic anti-tank capability, requiring no special deployment or support. Japanese tanks could no longer exploit mobility advantages when every position potentially concealed weapons capable of one-shot kills. The technical analysis Japanese engineers conducted on captured bazooka rockets revealed manufacturing quality that seemed almost wasteful by Japanese standards of resource conservation. Warhead bodies were pressed from single steel stampings with minimal machining, yet dimensional tolerances remained tight enough to ensure reliable performance. Copper cone liners showed no evidence of hand finishing, suggesting automated manufacturing processes. Even the electrical wiring and battery contacts used standardized components requiring no custom fitting. American industry had achieved what Japanese manufacturers considered contradictory: high-quality weapons manufactured with low-skill labor at minimal unit cost. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Japanese attempts to develop indigenous rocket launchers during 1945 faced obstacles that transcended simple engineering challenges. The Type 4 rocket launcher, designated for development in March 1945, aimed to create a weapon comparable to the bazooka using available Japanese materials and manufacturing capabilities. Initial designs called for a 70mm launcher firing shaped charge rockets, with approximately 80mm of penetration capability. This would prove adequate against most Allied light tanks but marginal against Sherman medium tanks featuring frontal armor approaching 3 inches thick when accounting for sloping. The development program immediately encountered material shortages that proved insurmountable. Copper for shaped charge liners competed with electrical system production for remaining aircraft and ships. High-quality steel tubing for launcher tubes required manufacturing capacity allocated to artillery barrel production. Even basic electrical components, batteries, wiring, and switches had become scarce as Japan's chemical and metallurgical industries collapsed under sustained American bombing. Engineers produced prototype launchers using whatever materials remained available, resulting in weapons that worked adequately in controlled testing but proved unreliable under field conditions. Chemical explosive production presented equally intractable problems. Japanese munitions plants manufactured picric acid-based explosives that had served adequately for conventional artillery shells and bombs. But shaped charge warheads demanded more powerful explosives with consistent detonation characteristics. Japanese chemists understood theoretically that compounds like RDX offered superior performance, but manufacturing such explosives required chemical plants with precise temperature control, continuous electrical power, and abundant raw materials. By mid-1945, American bombing had destroyed or damaged most major chemical facilities, while remaining plants operated intermittently due to power shortages and lack of feedstock materials. The production timeline for any Japanese rocket launcher program, assuming all technical problems could be solved, extended well beyond any realistic assessment of remaining war duration. Optimistic estimates suggested limited production might begin by January 1946, with meaningful quantities reaching combat units by mid-year. But by August 1945, Japanese military planners understood that homeland invasion would likely commence by November, and the nation's ability to sustain resistance beyond spring. 1946 appeared doubtful at best. Japanese intelligence assessments during summer 1945 attempted to project how American forces would employ bazookas during homeland invasion operations. The projections made grim reading. American infantry divisions would likely include organic bazooka teams at company and platoon levels, providing multi-layered anti-tank defenses that Japanese armor could not penetrate or suppress. Beach defenses would face landing craft equipped with rocket launchers capable of engaging fortified positions from offshore. Urban combat, where Japanese planners hoped defensive advantages would offset material inferiority, would instead favor American infantry carrying weapons effective at short ranges against any target, including concrete fortifications. The captured Bazooka forced Japanese military leadership to confront uncomfortable questions about fundamental strategic assumptions. Japan had committed to war in December 1941, based partly on assessments that American industrial power, while vast, could not be effectively mobilized for military purposes. The Bazooka represented a devastating counterexample, a weapon conceived, designed, tested, manufactured by the hundreds of thousands, and deployed globally within 3 years. American industry had not merely mobilized but had innovated at speeds Japanese planners considered impossible. This realization extended beyond weapons to encompass entire industrial systems. The Bazooka required sophisticated explosive chemistry, precision, metalworking, standardized electrical components, and coordination among multiple manufacturers, producing components assembled into complete weapons. American industry executed this complex choreography while simultaneously producing aircraft, ships, vehicles, artillery, and every other category of military equipment in overwhelming quantities. Japan's industrial base, which had seemed adequate in 1941, proved unable to match even a fraction of this output while maintaining quality standards. The psychological dimension of examining captured American weapons in August 1945 carried weight that transcended technical analysis. Japanese officers, studying the Bazooka, understood they were examining evidence of inevitable defeat. The weapon itself was merely one manifestation of industrial and technological superiority, so comprehensive that Japanese victory had become materially impossible, regardless of spiritual strength or tactical excellence. This represented a profound contradiction of core assumptions underlying Japanese military culture, which emphasized willpower and moral superiority over material considerations. Colonel Nakamura's final report to Army headquarters, completed on August 24, 1945, included recommendations that implicitly acknowledged Japan's hopeless situation. He advised that remaining tanks be deployed exclusively in static defensive positions, where they could engage approaching American forces from prepared positions with supporting infantry. Mobile operations should cease entirely, as Japanese armor could not survive against American anti-tank weapons in fluid combat. Tank crews should receive training in infantry combat skills, anticipating the likelihood that vehicles would be destroyed or immobilized, requiring crew members to continue fighting as riflemen. These recommendations reversed decades of Japanese armor doctrine development. Tanks had been conceived as offensive weapons, emphasizing mobility and shock action. Nakamura was advising their employment as pillboxes, negating every advantage Japanese tank designs had emphasized. The recommendations implicitly conceded that Japanese armor had failed to evolve adequately, that American anti-tank weapons had rendered mobile armored warfare suicidal for Japanese forces, and that remaining vehicles represented assets to be expended in static defense rather than preserved for decisive counterattacks. The broader implications troubled senior Japanese officers who understood military technology's trajectory. If American infantry now carried weapons defeating any practical armor thickness, what did this mean for future warfare? Tank design since World War I had followed an evolutionary path of increasing armor protection, but shaped charge technology appeared to have broken this progression. Armor could not be thickened sufficiently to defeat modern-shaped charges without creating vehicles too heavy to move. This suggested fundamental changes in how armored forces would operate, changes that Japan lacked time to implement. The Type 4 70mm anti-tank rocket launcher represented Japan's belated attempt to match American bazooka capabilities. Development began in late 1944 after Japanese forces encountered bazookas repeatedly across Pacific battlefields. The weapon featured innovative design elements, including spin stabilization through angled venturis in the rocket base, rather than aerodynamic fins. Testing showed the rocket could penetrate 80 millimeters of armor, less than both the Panzerschreck and the Bazooka, but still theoretically effective against Sherman tanks' side armor. The Type 4 launcher incorporated unique features reflecting Japan's constrained industrial situation. It was designed to be fired by a soldier while prone, with the gunner and loader lying at 45-degree angles to the bore. This configuration reduced the weapon's silhouette compared to shoulder-fired designs. The launcher split into two sections for transport, similar to the American 3.5-inch Super Bazooka developed late in the war. A bipod provided stability during aiming, and the firing mechanism used a spring-loaded hammer rather than electrical ignition, simplifying manufacturing requirements. But development speed could not compensate for Japan's collapsing industrial capacity. The weapon was reserved exclusively for homeland defense against the anticipated American invasion. Production never reached a meaningful scale before Japan's surrender in August 1945. The rocket reached velocities of 160 meters per second, faster than both the Bazooka and Panzerschreck, with an estimated hit ratio of 60% at 100 meters distance. Yet even these respectable performance figures came too late to influence combat outcomes. The weapon's design philosophy revealed how thoroughly American industrial practices had impressed Japanese engineers. The split-tube construction, prone firing position, and simplified ignition system all reflected attempts to create weapons manufacturable by Japan's degraded industrial base. Where American bazookas used standardized electrical components requiring functioning battery production, the Type 4 employed purely mechanical systems. Where American rockets used sophisticated fin stabilization requiring precision manufacturing, Japanese rockets used simpler spin stabilization. Every design choice represented an accommodation to industrial limitations that made direct copying of American technology impossible. Japanese chemical explosive development faced even more insurmountable obstacles. The Type 4 rocket warhead used conventional TNT-based explosives, the same basic formulations Japanese munitions plants had manufactured since the Russo-Japanese War. Attempting to synthesize RDX or equivalent high-performance explosives would have required chemical plants with capabilities Japan no longer possessed. Strategic bombing had destroyed or severely damaged most major chemical facilities by mid-1945. Remaining plants operated intermittently due to power shortages, lack of raw materials, and worker attrition. The copper shortage particularly constrained Japanese-shaped charge development. Every shaped charge warhead required high-purity copper for the cone liner, material increasingly scarce as naval blockade severed access to overseas copper sources. Japanese refineries struggled to produce copper-meeting electrical conductor specifications, much less the oxygen-free high-conductivity material American ordnance engineers specified for bazooka warheads. Engineers considered substitute materials, including steel and aluminum, but testing showed these alternatives produced inferior penetration performance. The broader context of Japan's August 1945 situation made weapons development almost irrelevant to strategic outcomes. American strategic bombing had devastated Japanese cities and industrial infrastructure. The naval blockade had reduced merchant fleet tonnage to levels inadequate for sustaining even basic economic activity. Soviet entry into the war on August 8 created a two-front nightmare that Japanese military planning had desperately sought to avoid. Within this context, analyzing captured bazookas and developing indigenous rocket launchers represented efforts that could not materially alter Japan's trajectory toward inevitable defeat. The psychological impact of the bazooka analysis extended beyond immediate tactical concerns. Japanese officers examining captured American weapons understood they were documenting evidence of comprehensive industrial and technological defeat. The bazooka was merely one manifestation among thousands. American forces deployed superior aircraft, ships, vehicles, artillery, communications equipment, and logistics systems across every category of military hardware. The cumulative effect demonstrated industrial advantages so overwhelming that Japanese victory had become materially impossible, regardless of willpower or tactical skill. This realization contradicted fundamental assumptions underlying Japanese military culture since the Meiji Restoration. Japanese martial tradition emphasized spiritual factors, warrior spirit, and moral superiority, over material considerations. The narrative sustaining Japanese military efforts since December 1941 held that superior fighting spirit would overcome American industrial advantages. Examining the bazooka forced Japanese officers to confront the reality that no amount of fighting spirit could compensate for 5-to-1 disadvantages in armor penetration capability, 4,000-to-1 disadvantages in industrial production capacity. Colonel Nakamura's technical reports from August 1945 survive in fragmentary form, much having been destroyed during Japan's surrender. However, post-war interrogations and captured documents reveal the conclusions Japanese ordnance experts reached. The bazooka represented weapon technology Japan could neither match nor effectively counter given existing capabilities. Japanese armor was obsolete. Japanese anti-tank weapons lagged years behind American equivalents. Most significantly, Japan's industrial infrastructure had deteriorated beyond the point where technological gaps could be closed through engineering innovation alone. The timing added bitter irony. By the time Japanese engineers completed comprehensive bazooka analysis, American atomic weapons had rendered conventional warfare considerations largely academic. The Hiroshima bombing on August 6 and Nagasaki bombing on August 9 demonstrated destructive capabilities that made arguments about tank armor thickness seem quaint. Japan surrendered on August 15, just days after Colonel Nakamura's final technical reports reached Army headquarters. The captured bazookas that prompted such intensive study never faced Japanese tanks in combat on the homeland. Post-war analysis by American ordnance experts examining Japanese Type 4 rocket launcher prototypes acknowledged the clever engineering solutions Japanese designers had devised under severe constraints. The spin-stabilized rocket represented innovative thinking that would later influence Chinese rocket launcher development during the Korean War. When the Chinese reverse-engineered the American M20 super bazooka in the Korean War to produce the Type 51 90mm rocket launcher, they used data from the experimental Type 4 anti-tank rocket launcher left at the 52nd Military Arsenal in Shenyang, formerly the Imperial Japanese Army South Manchuria Arsenal. But acknowledging engineering cleverness should not obscure the fundamental reality. Japanese rocket launcher development in 1945 represented desperate improvisation by a defeated nation attempting to develop weapons for battles that would never occur. The Type 4 existed primarily as testimony to how thoroughly Japan had lost the industrial race that determined World War II's outcome. Every technical specification, every design compromise, every manufacturing shortcut documented Japan's inability to match American industrial capabilities that made weapons like the bazooka possible. The captured bazooka's legacy extended far beyond its immediate tactical impact. The weapon demonstrated principles that would govern anti-tank warfare for decades. Shaped charge technology proved that armor protection faced fundamental limits. No practical thickness could defeat hypervelocity jets moving at 25,000 feet per second. This realization drove post-war tank design toward composite armor, reactive armor, and active protection systems attempting to defeat shaped charges through means other than simple thickness increases. Soviet weapons. Designers studying captured American and German rocket launchers developed the RPG series that became ubiquitous across Cold War conflicts. The RPG-7, introduced in 1961, incorporated aluminum powder in its warhead explosive, a direct lineage back to George Kistakovsky's forbidden chemistry developed at Harvard in 1943. Modern anti-tank weapons, from American Javelin missiles to Chinese HJ series systems, all employ shaped charge warheads, whose fundamental principles were established during World War II bazooka development. The Japanese experience examining captured bazookas illuminated broader truths about technological competition in modern warfare. Superior weapons design mattered, but industrial capacity to manufacture weapons at scale mattered more. Training and tactics mattered, but access to raw materials and functioning supply chains mattered more. Warrior spirit and tactical excellence could not compensate for material disadvantages, measured in orders of magnitude. These lessons, learned at terrible cost during World War II, continue shaping military planning today. For Japanese tank crews who survived the war, The memory of examining bazooka penetration holes in their best armor remained vivid decades later. They had trained in machines designed when Japanese military planners believed armor protection adequate and infantry portable anti-tank weapons impossible. They witnessed how rapidly technological change had rendered those assumptions obsolete. The Type 97 Chiha that seemed adequate in 1937 was hopelessly obsolete by 1944, not because Japanese engineering had failed, but because American industry had revolutionized anti-tank warfare in ways Japanese planners never anticipated. The bazooka represented more than a weapon. It embodied American industrial philosophy. Simple designs enabling mass production, standardized components allowing rapid manufacturing, scale-up, and performance specifications prioritizing effectiveness over elegance. Japanese weapons development traditionally emphasized precision manufacturing, hand-fitted components, and aesthetic refinement. These approaches produced excellent weapons in small quantities. American methods produced adequate weapons in overwhelming quantities. The outcome demonstrated which philosophy better suited industrial warfare's brutal mathematics. Japanese officers examining captured bazookas in August 1945 understood they were witnessing the future of warfare, even as their nation faced immediate defeat. Infantry portable weapons could now defeat any practical armor thickness. This fundamentally altered relationships between infantry and armor that had governed ground combat since World War I. Tanks would remain important, but they could no longer dominate battlefields through armor protection alone. Every tank crew would face threats from infantry that previous generations of tankers never confronted. The psychological burden of this realization weighed heavily on Japanese armor officers who had devoted careers to tank warfare doctrine. Everything they had learned, everything they had taught, every tactical principle they had internalized, was being invalidated by technological change they could neither prevent nor match. Their tanks were obsolete, their tactics were obsolete, their understanding of armored warfare was obsolete. The captured bazooka made these truths inescapable. The final irony was temporal. By the time Japanese engineers completed their bazooka analysis, the weapon itself was becoming obsolete. American ordnance experts were already developing guided anti-tank missiles that would make unguided rockets seem primitive. Within 2 decades, shoulder-fired missiles with ranges exceeding 2,000 meters would replace bazookas in frontline service. The weapon Japanese engineers studied so carefully in August 1945 represented a transitional technology, revolutionary in 1943 but destined for replacement by 1960. Yet the principles remained constant. Shaped charge technology, first weaponized effectively in World War II bazookas, still governs anti-armor warhead design today. The industrial philosophy enabling rapid mass production of sophisticated weapons at minimal unit cost still defines successful military procurement. The recognition that infantry portable weapons could defeat heavy armor still shapes tank design and employment. The lessons Japanese officers learned examining captured bazookas in August 1945 remain relevant 8 decades later. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.